Approaching Neptune from across the vast distance of the outer solar system, the planet appears first as a pale blue dot among the stars, growing gradually larger over weeks of travel. The color intensifies as you draw closer, revealing the rich azure blue that gives Neptune its distinctive appearance. A shade created by methane in the upper atmosphere absorbing red wavelengths of sunlight. Around this distant blue giant, 16 moons trace their paths through the void, each one a world with its own character and story. Tonight, we travel to Neptune's realm to explore every strange moon orbiting this remote planet, beginning with the most remarkable of them all. The largest moon, Triton, orbits closer to Neptune than our moon orbits Earth, relative to their sizes, and from Triton's surface, the blue planet would dominate the sky. We descend now towards Triton's frozen surface, approaching a landscape that holds some of the coldest temperatures measured anywhere in the solar system. The ground below appears in shades of pink and white, colors that seem almost warm, but which conceal temperatures far colder than anywhere on Earth. This is where our journey begins, standing on frozen nitrogen ice beneath a black sky, exploring a world that should not exist where it does. You are listening to the Drowsy Astronaut, and tonight we begin a slow, unhurried exploration of Neptune's family of moons, from massive Triton to tiny distant objects barely holding on to their orbits. There is no rush in what follows, no information you need to remember by morning, just a gentle journey through some of the strangest worlds in the outer solar system. If you enjoy this exploration, consider leaving a comment about where you are listening from, and perhaps a like or subscription if the channel helps you rest. The surface of Triton stretches away in all directions, frozen solid at a temperature of about -235 degrees Celsius, cold enough to freeze air itself into solid form. This temperature places Triton among the coldest surfaces we have ever measured, colder than Pluto, despite orbiting much closer to the Sun. The extreme cold exists because Triton reflects most of the faint sunlight that reaches it, the bright, icy surface sending heat back into space before it can warm the ground. Standing here, the cold would be absolute, far beyond anything Earth's polar regions could approach, a cold that makes steel brittle and would freeze any Earth substance solid. The nitrogen ice that dominates much of Triton's terrain creates plains that extend for hundreds of kilometers without significant variation. These plains appear smooth from a distance, though up close the surface shows subtle textures and variations in color. The smoothness tells us something important about this moon. The surface is young in geological terms, not heavily cratered like ancient worlds that have remained unchanged for billions of years. Something has been erasing the impact craters that should accumulate over time, resurfacing the landscape with fresh material that covers the scars of asteroid and comet impacts. The pink or salmon color visible in many regions comes from organic molecules called tholins, complex carbon-based compounds created when solar ultraviolet light and cosmic rays strike simpler molecules on the surface. These tholins form gradually over millions of years, their reddish-brown color mixing with the white nitrogen ice to create the distinctive hues. The color varies across the surface, some areas appearing almost white where fresh nitrogen frost has recently deposited, others showing deeper pink or tan where tholins have accumulated in higher concentrations. The interplay of white ice and pink organic material creates a mottled appearance, a landscape that would look alien and beautiful to eyes accustomed to Earth's browns and greens. Water ice exists on Triton as well, though it plays a different role here than on warmer worlds. At Triton's extreme temperature, water ice becomes as hard as granite, providing the structural foundation beneath the more volatile nitrogen ice. The water ice never melts, never flows, simply sits frozen in the crust for billions of years while other ices sublime and redeposit around it. This creates a layered structure where different types of ice occupy different roles, some providing structure, while others create the active surface we observe. The terrain includes features that planetary scientists have given descriptive names that convey their unusual nature. Regions called cantaloupe terrain show a bumpy, dimpled texture that resembles the skin of a cantaloupe melon, though on a much larger scale. Each dimple or cell in this terrain measures roughly 20 to 30 kilometers across, creating a regular pattern unlike anything seen on other planetary surfaces. The origin of this texture remains debated, with theories involving ice rising and sinking in slow convection patterns, or perhaps nitrogen ice expanding and contracting in response to seasonal temperature changes. Long fractures cut across Triton's surface, valleys and ridges that extend for hundreds of kilometers in relatively straight or gently curving paths. These features formed when the icy crust cracked under stress, possibly from tidal forces when Triton's orbit was still changing shape, or perhaps from internal expansion as the moon froze and the ice expanded. The fractures create walls and cliffs where different layers of ice are exposed. Though from orbit, these features appear as dark or bright lines against the surrounding terrain. Walking along one of these fractures would mean standing at the edge of cliffs, perhaps several hundred meters high, looking down into valleys carved in frozen nitrogen and water. The reflectivity of Triton's surface is among the highest measured anywhere in the solar system, with roughly 76% of sunlight being reflected back into space. This high reflectivity, called albedo in scientific terms, contributes to keeping Triton so extraordinarily cold, despite some internal heat sources. Most of the weak sunlight that reaches this distance from the sun simply bounces off the white and pink surface, never warming the ground. Only about 24% of the light is absorbed, barely enough to maintain the surface at temperatures where nitrogen can occasionally sublime into gas. Dark streaks mark the surface in various locations, appearing as smudges or trails extending across the brighter ice. These streaks tell a story of activity that we will explore more fully shortly. But their presence indicates that Triton is not a completely dead world. The streaks appear dark because they consist of material different from the surrounding nitrogen ice, possibly organic compounds or silicate dust deposited on the surface by processes operating beneath the ice. The length and orientation of the streaks provide clues about wind patterns in Triton's tenuous atmosphere, carrying particles downwind from their source. The surface temperature of -235 degrees Celsius translates to about 38 degrees above absolute zero, measured in the Kelvin temperature scale that scientists use. Absolute zero, the coldest possible temperature, sits at -273.15 degrees Celsius. So Triton's surface is only about 38 degrees warmer than the theoretical limit. At these temperatures, molecular motion slows dramatically. Gases condense into liquids and then solids, and material properties change in ways unfamiliar from everyday experience. Rubber would shatter like glass, air would be frozen solid, and metals would become superconductors if they were pure enough. Standing on this frozen surface, you would sink slightly into nitrogen frost that behaves like powdery snow, though far colder and drier than any snow on Earth. The gravity pulling you down is only about 8% of Earth's gravity, weak enough that you could jump several meters high with minimal effort. The horizon curves away more sharply than Earth's horizon because Triton is smaller, with a radius of about 1,353 kilometers compared to Earth's 6,371. This means the horizon sits closer, perhaps only 3 kilometers away on flat terrain, giving the landscape a more intimate feeling than Earth's vast vistas. Neptune hangs enormous in the black sky overhead, never moving from its position because Triton is tidally locked, always showing the same face to the planet. The blue giant appears roughly 60 times larger in Triton's sky than the Moon appears from Earth, a massive presence that dominates the view. From certain locations on Triton's surface, Neptune would appear directly overhead at the zenith, while from other locations, it would hover near the horizon. The planet goes through phases as seen from Triton. New Neptune when the Sun is behind the planet, crescent and gibbous as the angle changes, full Neptune when Triton is between the Sun and Neptune. The Sun itself appears as a brilliant point of light. Rather than the disk we see from Earth, its angular size much smaller due to Neptune's tremendous distance from our star. The sunlight at Neptune's orbit is roughly 900 times weaker than sunlight at Earth's distance, creating a perpetual twilight even at local noon. Despite this dimness, the high reflectivity of Triton's surface means the landscape is not pitch black, but rather evenly lit in soft white light that casts only gentle shadows. The black sky above shows stars clearly even during daytime. The lack of atmosphere, meaning no scattering, creates a blue sky. The surface shows very few impact craters, a remarkable characteristic for a world that has presumably existed for billions of years. Impact craters accumulate on airless worlds as asteroids and comets strike the surface, creating bowl-shaped depressions that persist indefinitely without erosion to wear them away. The scarcity of craters on Triton indicates the surface we see is geologically young, perhaps only 10 to 100 million years old in places. This means geological activity has resurfaced Triton relatively recently, covering over ancient craters with fresh material from the interior. Some craters do exist, particularly in certain regions that appear older than others, but even these show signs of modification and degradation. The edges are softened, the floors filled or deformed, suggesting that ice has flowed slowly over millions of years to blur their original shapes. The ice behaves differently at these cold temperatures than at Earth-like conditions, moving in viscous flow over geological timescales, even when it appears solid and static on human timescales. This gradual flow helps erase surface features, contributing to the relatively smooth appearance of much of Triton's terrain. The materials making up this frozen landscape include several different types of ice, beyond just nitrogen. Water ice, as mentioned, forms the bedrock and structural foundation. Its high strength at these temperatures allowing it to support mountains and valleys without collapsing. Carbon dioxide ice appears in some regions, frozen from the thin atmosphere during winter months. Methane ice exists in trace amounts, contributing to the pink coloration along with the organic tholins. The mixture of these ices creates a complex surface where different materials occupy different niches depending on temperature, pressure, and exposure to sunlight. Measurements from passing spacecraft have revealed that this surface sits atop an interior that remains mysterious in many ways. We know Triton has a rocky core, likely composed of silicate minerals similar to Earth's mantle rock, surrounded by layers of ice in various forms. The exact structure, the thickness of each layer, the state of the ice, whether liquid water exists anywhere in the interior, remains uncertain. What we can observe is the surface, this frozen landscape that preserves a record of recent geological activity and offers clues about what lies beneath. The temperature varies slightly across Triton's surface, depending on latitude and the angle of sunlight, though nowhere does it rise above the point where nitrogen ice would melt. The equatorial regions receive more direct sunlight and are slightly warmer, perhaps reaching -220 degrees Celsius at their warmest. The polar regions remain colder still, possibly dropping to -240 degrees or below during the long polar winter. These temperature variations drive seasonal changes in where ice accumulates and where it sublimes away, creating cycles that reshape the surface over Triton's long year. Triton's year, its orbital period around Neptune, takes 5.877 Earth days, less than a week by our calendar. This rapid orbit, combined with Triton's distance from the Sun, means the seasons are tied more to Triton's position relative to Neptune than to solar heating patterns. The geometry is complex because Neptune itself orbits the Sun once every 165 Earth years, creating long seasonal cycles where different parts of Triton face the Sun for decades at a time, before entering equally long periods of shadow. Looking across this landscape of frozen nitrogen and pink-stained ice, the combination of familiar and alien elements creates a scene both beautiful and strange. The smooth plains resemble snow-covered fields on Earth, but the color is wrong, the sky is black when it should be blue, and the massive blue planet hanging overhead never moves. The stillness is absolute, no wind disturbing the frost, except high in the thin atmosphere where gentle breezes carry dark particles across the surface. This is Triton's surface, one of the coldest places in the solar system, a world that holds secrets about Neptune's history and about the outer reaches of our planetary neighborhood. The frozen surface of Triton is not entirely still, despite the extreme cold and apparent desolation, a fact discovered when Voyager 2 flew past in 1989 and captured images of dark plumes rising from the ice. These plumes extend upward for several kilometers above the surface, narrow columns of gas and dust erupting from vents somewhere beneath the nitrogen frost. The discovery surprised scientists who had expected Triton to be geologically dead, frozen solid, with no internal heat to drive activity. Instead, the moon revealed itself as one of the few geologically active worlds in the outer solar system. The mechanism driving these eruptions involves solar heating in a process unlike volcanic activity on warmer worlds like Earth or Io. Sunlight, weak though it is at Neptune's distance, can penetrate through transparent nitrogen ice to a depth of perhaps 1 or 2 meters. This light gets absorbed by darker material beneath the clear ice, heating that material slightly above the surrounding temperature. The heat causes nitrogen ice beneath the surface to sublime directly from solid to gas, creating pockets of pressurized nitrogen that seek escape routes through cracks and weak points in the overlying ice. When the pressure builds sufficiently high, the nitrogen gas bursts through the surface like a geyser, carrying with it particles of the dark material that absorbed the original sunlight. The gas and dust mixture shoots upward at significant velocity. The low gravity and thin atmosphere, allowing it to reach heights of 8 kilometers or more before falling back. The pressure driving the eruption is not enormous by Earth standards, but is sufficient in Triton's environment to create spectacular displays that persist for extended periods, possibly months or years for individual vents. The dark particles carried aloft by the nitrogen geysers do not simply fall straight back down, but are caught by gentle winds in Triton's upper atmosphere. These winds, blowing at speeds of perhaps 10 to 20 meters per second, carry the particles sideways as they settle, depositing them downwind from the eruption site. Over time, this creates the dark streaks visible on Triton's surface, trails of material that can extend for over 100 kilometers across the white and pink ice. Each streak records the direction of the prevailing wind at the time the material was deposited. The composition of the dark material remains somewhat uncertain, limited by the inability to sample it directly with the instruments available during Voyager's brief flyby. The particles are likely organic compounds, tholins created by radiation processing of methane and nitrogen, mixed perhaps with silicate dust from the rocky interior beneath the ice. The dark color suggests carbon-rich material that absorbs sunlight effectively, which makes sense given that such material would be necessary to trigger the solar heating that drives the eruptions in the first place. The cycle becomes self-reinforcing. Dark material absorbs heat, causes eruptions, gets deposited on the surface where it absorbs more heat. Voyager 2 detected at least 4 active plumes during the brief time it spent imaging Triton's surface, suggesting that multiple vents were operating simultaneously. The plumes appeared as dark columns extending upward from specific points on the surface, their bases marking the location of the active vents. The tops of the plumes showed evidence of being sheared and carried downwind, creating the characteristic bent appearance of a column being blown sideways at its peak. The fact that multiple plumes were active during the short observation window suggests that eruptions are relatively common, not rare isolated events. The energy budget for these solar-powered geysers is modest compared to volcanic processes on warmer worlds, but it is sufficient, given Triton's extreme cold and low gravity. The sunlight reaching Triton delivers only about 1 watt of power per square meter, roughly 900 times less than Earth receives. Even a small fraction of this weak sunlight, trapped beneath transparent nitrogen ice, can generate enough heat to sublime the ice and create pressure. The low gravity means that gas pressure need not be as high to lift particles, and the thin atmosphere provides little resistance to their ascent. The seasonal nature of the eruptions likely means that activity varies depending on which parts of Triton are currently receiving sunlight. During southern summer on Triton, the southern hemisphere was tilted toward the sun, and this is where Voyager detected the active geysers. During northern summer, which lasts about 40 Earth years due to Neptune's long orbital period. The situation would reverse, with northern hemisphere vents becoming active, while southern ones enter dormancy. This seasonal cycle means different regions of Triton experience activity at different times, creating a complex pattern of resurfacing over centuries. The long-term effect of these eruptions is to gradually redistribute material across Triton's surface, moving dark organic particles from subsurface locations to the surface where they accumulate in streaks and eventually contribute to the overall surface composition. The process helps explain why Triton's surface appears so young, despite the Moon being billions of years old. The constant deposition of new material covers over impact craters and other features, creating the smooth plains we observe. The rate of resurfacing is slow by human timescales, but significant when integrated over millions of years. The discovery of active geysers on Triton placed the Moon in a small category of outer solar system bodies, showing ongoing geological activity. Io, Jupiter's innermost large moon, erupts with sulfur and silicate volcanism, driven by tidal heating from Jupiter's gravitational pull. Enceladus, a small moon of Saturn, shoots water ice geysers from its south pole, also likely powered by tidal heating. Europa, another Jupiter moon, may have similar activity, though geysers there remain less certain. Triton joins this select group with its nitrogen geysers, powered not by tidal forces, but by the distant sun's weak light. The implications of Triton's activity extend beyond simple geological interest to questions about the Moon's interior. If geysers are erupting through the surface, bringing material from below, what does this tell us about conditions beneath the crust? The presence of dark material suggests that Triton has a rocky core overlaid with ice, with organic compounds mixed throughout. The fact that nitrogen can accumulate in subsurface pockets implies layering in the ice, regions where material is trapped beneath less permeable layers above. Scientists have proposed that Triton may have a subsurface ocean of liquid water somewhere in its interior, kept liquid by a combination of residual heat from tidal interactions when the orbit was more eccentric, radioactive decay in the rocky core, and perhaps ongoing tidal flexing from Neptune. Such an ocean would be buried deep beneath the water ice crust, perhaps tens of kilometers down, and would not interact directly with the surface nitrogen ice. The evidence for this ocean remains indirect and uncertain, based on models of Triton's formation and evolution, rather than direct observation. The geysers themselves do not require a liquid ocean to operate, functioning perfectly well with solid ice throughout the crust heated locally by trapped sunlight. However, the overall level of geological activity suggested by the young surface age, the complex terrain features, and the ongoing eruptions points toward an interior that has remained warmer than would be expected from solar heating alone. The debate continues about how much internal heat Triton retains and what maintains it billions of years after the Moon's presumed formation. The dark streaks created by geyser deposits number in the hundreds across Triton's visible surface, creating a distinctive pattern that helps identify which hemisphere was in summer during Voyager's encounter. The streaks all point roughly in the same direction, indicating consistent wind patterns at the altitude where the geyser plumes reach their maximum height. This consistency suggests organized atmospheric circulation driven by temperature differences between Triton's sunlit and shadowed regions, with high-altitude winds flowing in patterns that persist over the months-long duration of active geyser season. Individual streaks vary in length from just a few kilometers to over 150 kilometers, reflecting differences in how long particular vents have been active and how much material they have erupted. Some streaks appear sharp and dark, suggesting recent deposition, while others are faded and less distinct, possibly older deposits that have been partially covered by fresh nitrogen frost or mixed with surrounding ice through slow churning processes. The variation creates texture in the surface appearance, breaking up the monotony of the white ice plains with dark features that catch the eye and raise questions about their origins. The geyser activity marks Triton as a world where processes still operate, where the frozen surface is not the end of the story, but rather a dynamic interface between the interior and space. Material cycles from below to above, gets modified by radiation and temperature, then perhaps works its way back down through surface collapse or slow burial by fresh ice. The timescales are long, decades to centuries for individual cycles. But the processes continue, making Triton a living world in the geological sense, if not the biological one. Looking at a dark streak extending across the pink-white nitrogen ice, you are seeing evidence of processes that happened recently by geological standards, possibly within the last few decades to centuries. The plume that created this particular streak erupted gas and dust that traveled upward for kilometers before being caught by winds and deposited along this path. The same processes may still be operating right now at this very moment. New plumes adding to existing streaks or creating new ones. The slow work of reshaping Triton's surface, continuing whether we watch or not. And beneath this active surface lies an orbit unlike any other large moon in the solar system, a backward path that tells its own remarkable story. Triton's orbit around Neptune follows a path that immediately marks this moon as unusual among the satellites in our solar system. While nearly all major moons orbit in the same direction their planet rotates, moving in the direction we call prograde, Triton orbits in the opposite direction, traveling retrograde around Neptune. This backward motion means that if you watched from above Neptune's north pole, you would see the planet spinning counterclockwise while Triton travels clockwise, moving against the expected flow. No other large moon in the solar system shares this characteristic. The orbit itself is nearly circular, with an eccentricity of only about 0.000016, making it almost a perfect circle. This circularity contrasts sharply with the elliptical orbits of many outer solar system moons and suggests that Triton's orbit has been modified over time. The distance from Neptune to Triton averages about 354,800 kilometers, roughly similar to the distance from Earth to our moon, but around a much more massive planet. The orbital period is 5.877 Earth days, meaning Triton completes one circuit around Neptune in just under 6 days. The combination of retrograde motion and near-circular orbit immediately tells planetary scientists that Triton did not form where it currently resides. Moons that form from the disk of material surrounding a young planet naturally orbit in the same direction the planet rotates, and typically in nearly circular paths close to the planet's equatorial plane. Triton's retrograde orbit violates this pattern so strongly that formation in place becomes essentially impossible. Instead, Triton must have originated elsewhere and been captured by Neptune's gravity at some point in the past. The leading theory for Triton's origin places its birthplace in the Kuiper Belt, the region of icy bodies beyond Neptune's orbit that includes Pluto and thousands of other objects. Triton's size, density, and composition all resemble what we observe for large Kuiper Belt objects, supporting the idea that Triton is essentially a captured dwarf planet. The surface composition, featuring nitrogen ice and organic tholins, closely matches what we see on Pluto, strengthening the connection between Triton and the Kuiper Belt population. The capture mechanism most likely involved a binary encounter, where Triton originally orbited in a pair with another object of comparable size. When this binary system passed close to Neptune, the gravitational interaction separated the pair, with one object gaining energy and escaping while the other lost energy and became gravitationally bound to Neptune. This three-body interaction can transfer orbital energy between the objects in ways that allow capture without requiring the improbable scenario of a single object being slowed by exactly the right amount during a single passage. After capture, Triton's initial orbit would have been highly elliptical rather than the nearly circular path we observe today. An elliptical orbit means that Triton's distance from Neptune would have varied significantly during each orbit, approaching close at periapsis and receding far at apoapsis. This variation in distance creates tidal forces, where Neptune's gravity pulls more strongly when Triton is closer and more weakly when it is farther away. These changing tidal forces flexed Triton's interior, generating heat through friction as the Moon was squeezed and released repeatedly during each orbit. The tidal heating from the elliptical orbit would have been substantial, possibly melting much of Triton's interior and allowing it to differentiate, with rocky material sinking to form a core and lighter ice rising to form the outer layers. At the same time, the tidal interaction between Neptune and Triton transferred energy from Triton's orbital motion to Neptune's rotation, gradually circularizing the orbit. The process took perhaps hundreds of millions of years, during which Triton slowly spiraled closer to Neptune, while its orbit became more and more circular. The tidal heating during this circularization phase may explain Triton's geological activity and young surface. The interior heat generated by tidal friction would have driven volcanic or cryovolcanic activity, resurfacing the Moon and erasing its earlier cratering history. Even after the orbit circularized and tidal heating diminished, the interior may have retained enough heat to power ongoing geological processes for billions of years. The residual heat, combined with heat from radioactive decay in the rocky core, could maintain Triton's activity even today. The retrograde orbit has another consequence that plays out over geological timescales. Triton is slowly spiraling inward toward Neptune. Tidal forces between the planet and the Moon transfer angular momentum in a direction determined by the orbit's direction. For a prograde Moon, this interaction pushes the Moon outward over time, as we see with Earth's Moon slowly receding from our planet. For a retrograde Moon like Triton, the interaction works in reverse, pulling the Moon inward. The rate is slow, only about 4 centimeters per year, but cumulative over millions and billions of years. Calculations suggest that in approximately 3.6 billion years, Triton will reach Neptune's Roche limit, the distance inside which tidal forces from the planet exceed the Moon's self-gravity. When Triton crosses this threshold, Neptune's tidal forces will tear the Moon apart, breaking it into countless fragments that will spread out around the planet. These fragments will form a magnificent ring system around Neptune, far more extensive than the faint rings that currently exist. Triton's destruction is thus inevitable, though distant enough in time that countless other changes will reshape the solar system first. The current orbital distance places Triton well outside Neptune's Roche limit, in a stable configuration that will persist for billions of years before the final inward spiral accelerates. The Moon is tidally locked to Neptune, meaning the same hemisphere always faces the planet, just as the same side of our Moon always faces Earth. This tidal lock-in occurred early in Triton's capture history, when tidal forces were strong and could quickly slow the Moon's rotation to match its orbital period. From Triton's surface, Neptune never appears to move in the sky, remaining fixed at the same position, depending on your location on the Moon. The retrograde orbit means that sunrise and sunset on Triton occur in the opposite direction from what we might expect by comparison to Earth. If we define Neptune's rotation as creating a standard for east and west, then the sun rises in Triton's west and sets in its east, backward from Neptune's own day-night cycle. This directional reversal is purely a matter of perspective and definition, but it emphasizes how Triton moves contrary to nearly everything else in Neptune's neighborhood. The capture event that placed Triton in its retrograde orbit almost certainly disrupted any moon system that Neptune may have had before. Models suggest that Neptune likely possessed several regular moons formed from the planet's circumplanetary disk, orbiting prograde in the equatorial plane, like the inner moons of other giant planets. When Triton was captured and began its early, highly eccentric orbit, gravitational interactions would have perturbed these earlier moons, possibly ejecting them from the system or causing collisions. The current small inner moons may be second-generation satellites, formed from the debris of this disruption. The timing of Triton's capture remains uncertain, but likely occurred in the first billion years of solar system history, when more large objects were still wandering in unstable orbits. The capture may have been relatively early, allowing time for the orbit to circularize and for geological processes to reshape the surface. Alternatively, some models suggest capture could have happened later, perhaps during a period when planetary migration stirred up the outer solar system and sent Kuiper Belt objects on paths that crossed the giant planet's orbits. Looking at Triton from Neptune, an observer would see the Moon moving across the sky in the opposite direction from the planet's rotation, rising in the west and setting in the east. The motion would be stately and slow due to the 5.877-day orbital period, taking about 3 Earth days to cross from horizon to horizon. During each orbit, Triton would go through its phases, from new when it passes between Neptune and the Sun, to full when Neptune lies between Triton and the Sun, the blue planet casting shadows across the Moon's nitrogen ice. The story told by Triton's retrograde orbit is one of capture and transformation, of a Kuiper Belt wanderer becoming a planetary satellite, of gravitational interactions powerful enough to melt interiors and reshape surfaces. The orbit continues to evolve, drawing Triton slowly but inexorably toward its eventual destruction. though that ending lies so far in the future that intervening events may change the scenario in unexpected ways. For now, Triton orbits backward around Neptune, unique among large moons, carrying in its motion the evidence of a violent and remarkable history. And as this frozen world travels its backward path, it drags with it a thin envelope of nitrogen gas, an atmosphere that cycles with the seasons and connects the surface to the space around it. The space immediately surrounding Triton is not quite empty vacuum, but rather filled with an extremely tenuous atmosphere composed primarily of nitrogen gas. This atmosphere extends upward from the frozen nitrogen ice on the surface, created as sunlight and subsurface warmth cause the ice to sublime directly from solid to gas without passing through a liquid phase. The surface pressure of this atmosphere measures about 14 microbars, which sounds like a number until we compare it to Earth's sea level pressure of 1 bar. Triton's atmosphere is roughly 1/70,000th the pressure of Earth's air, far thinner than the best vacuum we can create in terrestrial laboratories. Despite being so thin, this nitrogen atmosphere is real and plays important roles in shaping Triton's environment and evolution. The atmosphere scatters a small fraction of sunlight, creating a very faint haze that softens shadows slightly compared to the stark blackness we see on completely airless bodies like our moon. The atmosphere allows sounds to propagate, though they would be extremely faint and high-pitched due to the low density and molecular composition. Standing on Triton, you would effectively be in a vacuum for practical purposes, requiring a pressure suit just as on the moon. But instruments could detect the presence of surrounding gas. The nitrogen that makes up most of Triton's atmosphere exists in equilibrium with the nitrogen ice on the surface, subliming when conditions warm slightly and condensing back to solid when they cool. This equilibrium means the atmospheric pressure varies with temperature, increasing slightly during Triton's summer when more sunlight reaches the surface, and decreasing during winter as nitrogen freezes out. The seasonal pressure variations can be substantial, potentially doubling or halving the atmospheric density between summer and winter at any given location. These changes unfold slowly over Triton's long seasonal cycle, with each season lasting about 40 Earth years. Nitrogen molecules in the atmosphere move rapidly. Despite the low temperature, their speeds determined by thermal energy rather than atmospheric density. At 38 Kelvin, nitrogen molecules zip about at roughly 230 meters per second, much slower than at room temperature, but still fast enough to create what physicists call a gas rather than just stationary matter. When these molecules collide with each other or with the surface, they exchange energy and momentum, gradually redistributing material and heat through the system. The collision rate is low compared to Earth's atmosphere, but sufficient to create observable effects over time. Above the surface layer, the atmosphere extends upward for several hundred kilometers before thinning to the point where it merges with the interplanetary environment. The density decreases exponentially with altitude, according to a scale height of about 60 kilometers, meaning that every 60 kilometers upward reduces the density by a factor of roughly 2.7. This relatively large-scale height, compared to Earth's 8-kilometer scale height, reflects nitrogen's low molecular weight and Triton's weak gravity, which allows the atmosphere to puff up more than it would on a more massive world. Within this extended atmosphere exists an ionosphere, a region where solar ultraviolet radiation has enough energy to strip electrons from nitrogen molecules, creating electrically charged ions and free electrons. The ionosphere begins at altitudes of perhaps 300 to 400 kilometers and extends upward, marking the transition from neutral atmosphere to ionized upper layers. The charged particles in the ionosphere can interact with Neptune's magnetic field, though the details of this interaction remain poorly understood due to limited observations during Voyager's brief encounter. Temperature in Triton's atmosphere shows an unusual structure that planetary scientists call a temperature inversion. Near the surface, the temperature hovers around 38 Kelvin, matching the temperature of the nitrogen ice that feeds the atmosphere through sublimation. Moving upward through the lower atmosphere, temperature initially drops slightly, as expected from expansion cooling. However, at higher altitudes in the thermosphere, absorption of solar ultraviolet radiation heats the gas to temperatures approaching 95 Kelvin, more than twice the surface temperature. This creates a warm layer above a cold layer, the opposite of what we see in Earth's troposphere. The warm thermosphere seems paradoxical when we consider how little solar energy reaches Neptune's distance from the Sun. The explanation lies in the extremely low density of the upper atmosphere, which means that even a small amount of absorbed energy can raise the temperature significantly because so few molecules are present to share the energy. Temperature in a gas reflects the average kinetic energy of molecules, and with very few molecules present, a small energy input creates large temperature increases. The practical result is that the thermosphere is hot by temperature measurement, but contains almost no heat energy by total energy content. Winds exist in Triton's atmosphere, driven by temperature differences between the sunlit hemisphere and the shadowed regions, and by the seasonal migration of nitrogen between different latitudes. The wind speeds measured indirectly from the direction of geyser plume deposits suggest velocities of 10 to 20 meters per second at the altitudes where the plumes reach their maximum height. These speeds are modest by Earth standards, but significant in Triton's low-density environment. The winds carry the dark particles erupted from geysers sideways across the surface, creating the streaks we observe and providing visible evidence of atmospheric circulation patterns. The atmospheric circulation likely involves large-scale patterns where gas sublimes from the warmer, sunlit regions and flows toward colder areas where it condenses back to ice. This creates a net transport of nitrogen from summer to winter hemispheres, gradually shifting mass across Triton's surface over the 40-year seasonal cycle. When the seasons reverse, the flow reverses as well, carrying nitrogen back in the opposite direction. Over many seasonal cycles, this back and forth transport may eventually even out, but local imbalances can persist for centuries. Trace constituents in the atmosphere, beyond the dominant nitrogen, include methane, which makes up perhaps 0.1% or less of the total, and carbon monoxide in even smaller amounts. These trace gases are also present as ices on the surface and sublime along with nitrogen when temperatures rise. The methane can be broken down by solar ultraviolet radiation into simpler hydrocarbons and eventually into the organic tholins that color Triton's surface. The photochemistry happening in the atmosphere contributes to the production of the complex organic molecules we see coating the ice. creating a slow but continuous chemical evolution of the surface composition. Haze layers may exist at certain altitudes in Triton's atmosphere, formed by condensation of trace gases or by accumulation of tiny particles created through photochemistry. Models predict that such hazes would be most prominent at heights of 20 to 40 kilometers above the surface, though Voyager's cameras did not clearly detect them. The hazes, if present, would consist of extremely fine particles, almost molecular in size, scattering light in ways that could make them visible against the dark sky background when viewed from the right angle. The existence of an atmosphere on Triton places it in a small category of moons that maintain substantial gaseous envelopes despite their relatively small size and distance from the Sun. Saturn's moon Titan has a thick nitrogen atmosphere, far more substantial than Triton's, but similar in composition and driven by similar processes of surface-atmosphere exchange. Jupiter's moon Io has a thin atmosphere of sulfur dioxide created by volcanic outgassing. Saturn's moon Enceladus may have a transient atmosphere fed by its south polar geysers. Triton joins this group, demonstrating that atmospheres can exist under surprisingly diverse conditions if the right ingredients and energy sources are present. The similarity between Triton's nitrogen atmosphere and the nitrogen atmospheres of Pluto and other large Kuiper Belt objects further supports the theory that Triton originated in that region. Both Triton and Pluto maintain surface pressures in the tens of microbars range. Both have nitrogen ice on their surfaces, and both experience seasonal atmospheric pressure changes as nitrogen sublimates and condenses with changing solar illumination. The parallel suggests common origins and similar evolutionary pathways, despite Triton's subsequent capture by Neptune changing its environment dramatically. Looking up from Triton's surface into this thin nitrogen atmosphere, the view transitions smoothly from the surface ice to the faint haze near the ground to the blackness of space above. Stars remain visible even at noon, their light barely scattered by the tenuous air. Neptune looms overhead, the blue planet's appearance unchanged by the thin atmosphere, except perhaps for the faintest softening of its edge. The atmosphere is there, surrounding you, cycling between surface and space, carrying particles from geysers to distant deposition sites. But it imposes no barrier to your view of the universe beyond. And that view includes not just Neptune, but its other moons, including Proteus, the second largest moon that remained hidden from human eyes until the space age brought telescopes into the outer solar system. Proteus orbits Neptune well inside Triton's path, traveling closer to the blue planet than its much larger sibling, following a path that brings it near enough to Neptune that the planet's gravitational influence dominates everything about this moon's environment. The moon appears dark, even by outer solar system standards, reflecting only about 6% of the sunlight that reaches it, making it blend into the blackness of space when viewed from any significant distance. This darkness, combined with its proximity to Neptune's overwhelming glare when seen from Earth, meant that Proteus remained completely unknown until Voyager 2's cameras revealed it during the 1989 encounter, making it one of the last major moons in the solar system to be discovered. The size of Proteus places it firmly in the category of substantial moons, despite it being Neptune's second largest by a wide margin. The moon measures roughly 420 kilometers across its longest axis, though the exact dimensions vary because Proteus is not spherical, but rather irregularly shaped. The three axes measure approximately 424 kilometers, 390 kilometers, and 396 kilometers, creating a lumpy, potato-like form rather than the smooth ball that larger moons achieve. This irregular shape places Proteus right at the boundary where an object's self-gravity becomes strong enough to pull it into a sphere, a threshold that depends on composition, internal structure, and rotation rate. The surface of Proteus appears heavily cratered when viewed in the images Voyager captured during its brief flyby, though the resolution limits what details we can discern. Craters of various sizes cover the visible hemisphere, overlapping in places where newer impacts struck areas already marked by older ones. The crater density suggests the surface is ancient, likely dating back billions of years to the early solar system, when impact rates were much higher than today. No evidence appears for geological resurfacing, volcanic activity, or tectonic deformation that might have erased craters, indicating that Proteus froze geologically not long after its formation. One crater dominates the landscape in a way that immediately draws attention, even in low-resolution images. Named Pharos after the famous lighthouse at Alexandria, this enormous impact feature measures roughly 255 kilometers in diameter, spanning more than half the width of Proteus itself. The impact that created Pharos must have come close to destroying Proteus entirely, delivering energy sufficient to fracture the moon, or perhaps even to shatter it completely. That Proteus survived indicates either fortunate circumstances in the impact geometry or structural properties that allowed the moon to absorb the shock without fragmenting. The walls of Pharos crater rise above the surrounding terrain, creating a bowl-shaped depression with a well-defined rim visible in Voyager's images. The floor of the crater appears relatively flat or gently rolling, lacking the central peak that often appears in large impact craters on other worlds. The absence of a central peak may reflect Proteus's composition and internal structure, or it may indicate that the impact occurred when Proteus was still partially molten, allowing the crater floor to relax and flatten over time. The crater's size, relative to Proteus, means that standing at one rim, the opposite rim would be beyond the horizon, hidden by the curvature of this small world. Additional large craters mark Proteus's surface, though none approach Pharos's scale. These smaller impacts, ranging from tens to perhaps 100 kilometers across, testify to a long history of bombardment by asteroids and comets passing through Neptune's neighborhood. Each crater represents a violent collision that occurred sometime in the past 4 billion years. A moment when rock or ice traveling at kilometers per second struck Proteus and excavated material from beneath the surface. The fact that these craters remain well preserved indicates minimal erosion or modification since they formed. The dark color of Proteus's surface likely results from a coating of carbon-rich organic compounds, similar to the tholins found on Triton, but without the brighter nitrogen ice to lighten the overall appearance. The organics form when simpler molecules like methane are broken apart by solar ultraviolet radiation and cosmic rays, with the fragments recombining into increasingly complex carbon-based molecules. Over billions of years, this process can darken a surface significantly, converting initially grey ice into charcoal black material. The low reflectivity makes Proteus one of the darkest objects in the solar system, comparable to fresh asphalt or charcoal in terms of how much light it reflects. Beneath this dark surface lies an interior that we can only infer from Proteus's size, mass, and behavior. The density, measured from gravitational effects during Voyager's flyby, suggests a composition of water ice mixed with rocky material, perhaps about half ice and half rock by mass. This composition matches what we expect for objects that formed in the outer solar system, where water, ice was abundant and could mix with silicate and carbonaceous materials. The interior is probably not differentiated into distinct layers, meaning rock and ice remain mixed together rather than having separated, with rock sinking to form a core and ice rising to form a mantle. The temperature at Proteus's surface can be estimated from its distance from the Sun and its albedo, though direct measurements were not made during Voyager's encounter. At about 51 Kelvin, or minus 222 degrees Celsius, the surface is cold enough to keep water ice frozen solid for all time, and to allow other volatile ices to persist if they were ever present. This temperature places Proteus significantly warmer than Triton, despite being closer to the Sun, a seemingly paradoxical result that reflects Triton's higher reflectivity, bouncing more sunlight back into space. Proteus's dark surface absorbs more heat, leading to slightly higher temperatures despite similar solar illumination. The orbital characteristics of Proteus reflect its position as an inner moon, circling Neptune at a distance of about 117,600 kilometers from the planet's center. This places Proteus outside Neptune's rings, but well inside Triton's orbit, in a region where Neptune's gravity exerts strong influence. The orbital period is just 1.122 days, or about 26.9 hours, meaning Proteus completes roughly 8 orbits during each Triton orbit. Like most moons, Proteus is tidally locked to Neptune, always showing the same face to the planet as it orbits. The orbit lies almost exactly in Neptune's equatorial plane and is nearly circular, characteristics typical of regular moons that formed from material orbiting the planet rather than being captured from elsewhere. This suggests Proteus is a native Neptunian moon, though it may have formed after Triton's capture disrupted any earlier moon system. The second-generation formation scenario would place Proteus's origin in the debris left after Triton's elliptical orbit cleared out or destroyed Neptune's original regular satellites. The material would have reaccreted into new moons, including Proteus, Larissa, and the other inner satellites we observe today. Proteus's proximity to Neptune means the planet appears enormous in its sky, subtending an angle of about 15 to 20 degrees, roughly 40 times larger than the Moon appears from Earth. The blue disk would dominate the view, showing cloud details and possibly the dark spot features that come and go in Neptune's atmosphere. From Proteus's perspective, Neptune never moves, remaining fixed in the same position due to tidal locking, while the Sun and stars wheel around the sky during each 26-hour day. The gravity on Proteus's surface is weak, only about 0.079 meters per second squared, roughly 0.8% of Earth's gravity. Standing on this surface, you could jump many meters high with minimal effort, and dropping an object would see it fall in slow motion, taking many seconds to descend distances that would take fractions of a second on Earth. Walking would be replaced by gentle, bouncing leaps, each step covering ground easily but requiring conscious control to avoid bounding too high and spending long seconds in flight before returning to the surface. The small moon's weak gravity means it can barely hold on to any impact ejector thrown up when asteroids strike its surface. Material excavated by impacts reaching speeds above a few hundred meters per second would escape Proteus entirely, flying off into orbit around Neptune, or even escaping the system completely. This creates an asymmetry where impacts remove material from Proteus over time, gradually wearing it down through billions of years of bombardment. The survival of Pharos and other large craters suggests this erosion has been limited, but over truly cosmic timescales, it may be significant. Looking across Proteus's dark cratered surface, with Neptune filling the sky, the scene evokes desolation and ancient stillness. A world that froze into its current form billions of years ago and has changed little since, except for the occasional impact adding a new crater to the collection. No atmosphere stirs the surface. No geological activity reshapes the landscape. No internal heat drives any process we can detect. Proteus simply exists, orbiting Neptune in its precise path. A dark, irregular moon, preserving a record of the outer solar system's violent youth. And far beyond Proteus's regular orbit, another moon follows a very different path, wandering on an elliptical trajectory, unlike anything else in Neptune's family. In the distant reaches of Neptune's gravitational influence, a moon called Nereid follows an orbit so eccentric that it ranks as the most elliptical path of any large moon in the entire solar system. The orbit's shape defies the circular paths we expect from objects that formed alongside their parent planets, instead tracing a long ellipse that carries Nereid from relative closeness to Neptune out to remote distances before returning inward again. The eccentricity value of 0.7507 describes this elongation mathematically, a number that planetary scientists recognize immediately as extraordinary for a moon, more typical of comets than regular satellites. At the closest point in its orbit, called periapsis, Nereid approaches Neptune to within about 1.37 million kilometers, a distance roughly 3.5 times the separation between Earth and our moon. At this close approach, Neptune's gravity pulls strongly on Nereid, accelerating the moon as it whips around the near point of its orbit. The planet appears large in Nereid's sky during these close passages, though still not as enormous as it appears from the inner moons that orbit much nearer. The close approach lasts for only a small fraction of Nereid's orbital period before the moon begins its outward journey. The outward leg of the orbit carries Nereid to an apoapsis distance of about 9.66 million kilometers from Neptune, nearly 7 times farther than the periapsis distance. At this remote point, Neptune appears much smaller, a distant blue disk rather than a dominant planetary presence. Nereid moves slowly through this outer portion of its orbit, spending most of its year far from Neptune, where orbital velocities are low. The vast majority of the time, Nereid exists in this cold, distant state, only briefly experiencing the relatively warmer, closer environment during periapsis passage. The complete orbital journey from periapsis back to periapsis takes Nereid 360.14 Earth days, just under 1 Earth year. This long period reflects the large average distance from Neptune and the laws of orbital mechanics that link period to distance. During this year-long circuit, Nereid experiences dramatic variations in its environment, from the relative warmth and brightness near Neptune to the cold isolation of apoapsis, where the sun's weak light grows weaker still. The seasonal cycle, if we can call it that, occurs once per Nereid year, rather than the longer seasonal patterns driven by planetary orbital motion around the Sun. The size of Nereid makes it Neptune's third largest moon at about 340 kilometers in diameter, larger than the inner moons like Proteus, but much smaller than Triton. The exact size remains somewhat uncertain because Voyager 2 passed too far from Nereid to obtain detailed measurements, and ground-based observations can only estimate the size from brightness and assumptions about albedo. The shape appears irregular rather than spherical, consistent with an object of this size whose gravity is too weak to pull it into a perfect ball. The non-spherical shape may result from Nereid being a rubble pile, a loosely assembled collection of fragments rather than a single solid body. Brightness measurements of Nereid from Earth reveal unusual variations as the moon rotates, changing by about 40% in reflected light over a cycle of roughly 11.5 hours. These variations could result from an irregular shape causing different cross-sections to face Earth as Nereid spins, or from surface markings where some regions are brighter than others. The rotation period of 11.5 hours is notably different from Nereid's 360-day orbital period, indicating that, unlike most moons, Nereid is not tidally locked to Neptune. This lack of tidal locking results from the eccentric orbit preventing the stable synchronous rotation that circular orbits enable. The rotation may even be chaotic rather than strictly periodic, tumbling in ways that change over time rather than maintaining a constant spin axis and rate. Chaotic rotation occurs when tidal forces from a planet vary significantly during each orbit, preventing the damping effects that normally slow a moon's rotation until it matches the orbital period. For Nereid, the factor of 7 variation in distance from Neptune creates wildly varying tidal forces that may prevent any stable rotational state from persisting. If the rotation is indeed chaotic, Nereid tumbles through space without a fixed rotation period, its orientation changing unpredictably. The surface of Nereid appears grey in colour, with a moderate albedo of about 0.24, reflecting roughly 24% of sunlight that reaches it. This brightness exceeds Proteus's dark 6% reflectivity, but remains far below Triton's brilliant 76%, placing Nereid in the middle range for outer solar system moons. The composition likely includes water, ice, mixed with darker rocky or carbonaceous material, the proportions creating the moderate overall reflectivity we observe. No detailed surface images exist to reveal terrain features, crater distributions, or geological structures, leaving Nereid's surface characteristics largely unknown. The extreme orbital eccentricity almost certainly indicates that Nereid is a captured object rather than a moon that formed in place around Neptune. An object forming from Neptune's circumplanetary disk would naturally settle into a circular orbit close to the planet's equatorial plane, the configuration that minimizes energy and angular momentum. Nereid's elongated orbit requires a different origin story, one involving gravitational capture or perhaps perturbation of an initially circular orbit by some major event. The retrograde capture of Triton may have provided exactly such a major event. The scenario involves Nereid originally occupying a more circular prograde orbit around Neptune, formed in the normal way from the planet's surrounding disk. When Triton was captured and settled into its initial highly elliptical orbit, gravitational interactions between the two moons could have scattered Nereid outward into its current eccentric path. Alternative scenarios suggest Nereid itself may be a captured Kuiper Belt object that happened to pass close enough to Neptune with the right velocity to become bound rather than escaping back to the outer solar system. The lack of detailed composition and surface data makes distinguishing between these scenarios difficult. Nereid's orbit crosses the paths of several of Neptune's outer irregular moons, creating the theoretical possibility of close approaches or even collisions over very long timescales. The orbital stability analysis suggests Nereid's path may not be perfectly stable over billions of years, with perturbations from the Sun and Neptune's other moons potentially altering the orbit slowly. Whether Nereid will remain on its current path indefinitely or eventually escape Neptune's gravitational influence or collide with another moon remains uncertain without more detailed dynamical modeling. The temperature at Nereid's surface varies depending on the moon's distance from Neptune and the Sun during different parts of its orbit. At apoapsis, when farthest from both Neptune and the Sun, temperatures may drop to as low as 40 Kelvin, cold enough to freeze virtually every volatile compound solid. At periapsis, slightly more solar heating and possibly some thermal radiation from Neptune might raise temperatures to perhaps 55 or 60 Kelvin. Still extraordinarily cold, but representing a temperature swing of 15 to 20 degrees during each orbit. The variation would cause interesting effects if any volatile ices exist on the surface, potentially creating seasonal sublimation and condensation cycles. From Nereid's perspective, during a close approach to Neptune, the planet grows from a distant blue dot to a substantial disk over the course of weeks as the moon accelerates inward. The maximum apparent size of Neptune in Nereid's sky is perhaps 3 degrees across at periapsis, about 6 times larger than the moon appears from Earth, but much smaller than Neptune appears from the inner moons. After periapsis passage, Neptune shrinks again as Nereid climbs back out toward apoapsis, the planet dwindling to a small disk and eventually a bright point among the stars. The view provides a constantly changing perspective on Neptune that no other moon experiences to such an extreme degree. The wandering orbit gives Nereid its name, derived from the Nereids, who were sea nymphs in Greek mythology, daughters of Nereus and companions of Poseidon, the Greek god corresponding to the Roman Neptune. The name captures the moon's wandering nature, swimming through Neptune's gravitational ocean on a path that takes it far from the planet before returning close. This poetic naming followed the tradition for outer solar system moons of drawing from mythology associated with the relevant planet's namesake deity. Looking toward Nereid from Neptune, an observer would see the moon brighten and dim over its year-long orbit, approaching and receding in a slow dance unique among Neptune's moons. The eccentric orbit makes Nereid a wanderer in the Neptune system, never settling into a simple circular path, carrying in its motion evidence of a capture event or gravitational disruption that occurred billions of years ago. And between Nereid's distant wandering and Triton's close retrograde orbit, Neptune hosts several small moons in tight, regular paths, shepherding the planet's faint rings and adding complexity to the inner system. Closer to Neptune than Proteus, orbiting in the region where the planet's faint rings spread through space, a collection of small moons follows precisely spaced paths through the darkness. These inner moons are much smaller than Triton or Proteus, measuring from roughly 200 kilometers down to less than 20 kilometers across, and all remained unknown until Voyager 2's cameras revealed them during the brief encounter in August 1989. The moons orbit in nearly circular paths close to Neptune's equatorial plane, moving in the same prograde direction as the planet's rotation, characteristics that mark them as regular satellites rather than captured objects. The innermost of these small moons is Nereid, orbiting at a distance of about 48,000 kilometers from Neptune's center, roughly one-third the way from the cloud tops to Proteus's orbit. Nereid measures about 96 kilometers along its longest axis and roughly 60 kilometers along its shortest, giving it an elongated potato-like shape that reflects its weak gravity and lack of mass to pull itself spherical. The orbital period is only about 7 hours, meaning Nereid completes more than 3 orbits around Neptune during a single Earth day. At this close distance, Neptune fills about 50 degrees of Nereid's sky, an overwhelming presence that dominates the view from every location on the small moon's surface. Just beyond Nereid orbits Thalassa, another irregularly shaped moon, measuring roughly 82 kilometers across its widest dimension. Thalassa circles Neptune every 7.5 hours at a distance of about 50,000 kilometers, traveling through its orbit only slightly outside Nereid's path. The two moons share similar characteristics: dark surfaces with low albedos around 6 to 10%, heavily cratered terrain visible in the limited resolution Voyager achieved, and irregular shapes indicating minimal or no differentiation of their interiors. The proximity of their orbits means gravitational interactions between them may occur over long timescales, though calculations suggest the orbits remain stable. Despina orbits farther out at roughly 52,500 kilometers from Neptune, completing an orbit every 8 hours. This moon is somewhat larger than Nereid or Thalassa, measuring about 150 kilometers in diameter, though still maintaining an irregular, non-spherical shape. The dark surface appears similar to the other inner moons, suggesting all share comparable compositions of water ice, mixed with dark organic material and possibly rocky components. The formation mechanism for these inner moons likely involved accretion from debris, following whatever disruption event cleared Neptune's original satellite system, possibly the capture of Triton, causing gravitational chaos. Galatea holds particular importance among the inner moons because of its role in Neptune's ring system. Orbiting at about 62,000 kilometers from Neptune, with a period of 10 hours, Galatea appears to act as a shepherd moon for Neptune's outermost ring, the Adam's ring that contains the unusual ring arcs. The moon's gravitational influence creates orbital resonances that confine material in certain locations within the ring, preventing the arcs from spreading uniformly around Neptune. Without Galatea's influence, the concentrated material in the arcs would gradually disperse, erasing the distinctive structure that makes Neptune's rings unique. Galatea measures about 176 kilometers in diameter, large enough that its gravity can affect nearby ring particles significantly. The resonance relationship involves Galatea completing exactly 42 orbits during the time material in the ring arcs completes 43 orbits, a 42 to 43 resonance that creates periodic gravitational nudges. These regular nudges shepherd the ring material, keeping particles confined to specific longitudes rather than spreading evenly. The mechanism demonstrates how even small moons can have dramatic effects on ring structure through precise orbital relationships. Larissa orbits farther out than Galatea at about 73,500 kilometers from Neptune, completing one orbit every 13 1/3 hours. This moon ranks as the largest of the inner group at roughly 194 kilometers in diameter, approaching but not quite reaching the size where gravity would pull it into a spherical shape. Larissa's existence was actually suspected before Voyager's arrival, based on a stellar occultation observation in 1981, when a star appeared to dim briefly as something passed in front of it. The observation suggested a moon, but could not confirm it definitively until Voyager's images revealed Larissa exactly where the occultation data predicted. The sixth and smallest known inner moon is Hippocamp, a tiny object only about 18 kilometers across, making it one of the smallest moons discovered anywhere in the solar system. Hippocamp was not found until 2013, when astronomers carefully examining archived Hubble Space Telescope images noticed a faint dot moving through the Neptune system. The moon orbits very close to Proteus, at about 105,000 kilometers from Neptune, inside Proteus's orbit, but outside the orbits of Nereid through Larissa. The proximity to Proteus and Hippocamp's tiny size suggests it may be a fragment knocked off Proteus by a comet impact in the relatively recent past, perhaps only a few million years ago. All these inner moons share the characteristic of being extremely dark, with albedos in the range of 6 to 10%, similar to Proteus. This darkness makes them blend into the blackness of space when viewed against Neptune's bright disk from Earth, explaining why none were discovered until spacecraft could observe from much closer range. The dark color likely results from organic material coating the surfaces, accumulating over billions of years as solar ultraviolet radiation and cosmic rays process simple molecules into complex, carbon-rich compounds. The coating turns initially gray ice into charcoal-black surfaces that absorb most incident light. The surfaces of these moons show crater densities that suggest ancient formation ages, with most having formed billions of years ago and experienced minimal geological modification since. The lack of atmosphere, geological activity, or significant tidal heating means that impact craters simply accumulate and persist indefinitely, creating the heavily cratered terrain visible in Voyager images where resolution permits. The crater distributions provide clues about the population of objects impacting Neptune's moons over solar system history, recording hits by asteroids, comets, and perhaps ejecta from impacts on other moons. The orbital positions of these inner moons place them in a dynamic environment where Neptune's strong gravity, tidal forces, and ring material all interact. The moons orbit inside the Roche limit for loose aggregates, meaning that if they were held together only by gravity rather than material strength, tidal forces from Neptune would tear them apart. The fact that they survive indicates they have at least some internal cohesion beyond simple gravitational binding. Though whether this makes them solid bodies or rubble piles held together by weak, cohesive forces remains uncertain. Tidal evolution affects these close-in moons, though the timescales are very long. Neptune's tidal bulge, raised by the Sun and Saturn to a tiny degree, interacts with each moon's gravity in ways that slowly alter orbits over millions of years. The direction and magnitude of orbital evolution depends on the specific orbital parameters and the tidal properties of Neptune itself, factors not well constrained by available data. Some theoretical work suggests these moons may be slowly spiraling inward toward eventual collision with Neptune or disruption within the Roche limit, though the timescales extend to billions of years. The temperature on these inner moon surfaces can be estimated from their distance from the Sun and Neptune, and from their low albedos that absorb most incident energy. Temperatures probably range from about 55 to 65 Kelvin, depending on the specific moon and whether it faces the Sun or is in Neptune's shadow. These temperatures keep water ice frozen solid and allow certain volatile ices to persist if they were present. Though the dark surfaces suggest any initially bright ices have been darkened by radiation processing over billions of years. From any of these inner moons, the view toward Neptune would be spectacular. The blue planet stretching across a significant fraction of the sky and showing cloud details visible to the naked eye. The Great Dark Spot, features that occasionally form in Neptune's atmosphere, would appear as obvious ovals rotating with the planet's 16-hour day. The rings would be visible edge-on as faint bands extending outward from both sides of Neptune's disk. Too faint to see easily, but detectable with patience. Other inner moons would appear as stars moving against the sky, their orbital motion carrying them past the fixed background of distant stars. These small dark moons represent a different class of objects from the large satellites Triton and Nereid, formed through different processes and experiencing different evolutionary paths. They are fragments and debris, second-generation moons created from the wreckage of whatever system Neptune originally possessed before Triton's capture rearranged everything. And they exist within and help maintain Neptune's faint ring system, delicate structures of dust and ice that reveal the ongoing dynamic processes in this distant planetary system. The space between Neptune's inner moons contains more than just empty vacuum. Faint rings of dust and ice circle the planet, invisible to telescopes from Earth, except under special circumstances, but revealed by Voyager 2's cameras when the spacecraft looked back at Neptune, with the Sun behind the planet. These rings form delicate bands of material orbiting in Neptune's equatorial plane, much fainter than Saturn's spectacular rings, but sharing similar physics in how gravity, orbital mechanics, and moonlet interactions shape their structure. The rings exist in a complex relationship with the inner moons, some providing material to the rings through micrometeorite impacts, others shepherding ring particles into confined regions through gravitational resonances. Neptune's ring system consists of 5 main components, named for astronomers and scientists who contributed to understanding Neptune. The innermost Galley ring, named for Johann Gottfried Galley, who first observed Neptune telescopically in 1846, orbits at about 42,000 kilometers from Neptune's center. This ring appears as a faint, broad band in Voyager images, extending from roughly 40,000 to 43,000 kilometers radius. The particles composing the ring are mostly dust-sized, too small to see individually, but collectively scattering enough light to create visible structure when viewed under ideal conditions. Beyond Gal lies the Leverrier ring, named for Urbain Leverrier, who mathematically predicted Neptune's existence before its telescopic discovery. This ring is narrower than Gale, orbiting at approximately 53,000 kilometers radius, with a width of perhaps 100 kilometers. The concentration of material creates a slightly brighter feature than the more diffuse Gale ring, though both remain extremely faint compared to the bright rings of Saturn. The gravitational influence of nearby moon Despina may help confine the Leverrier ring's particles, though the exact dynamics remain incompletely understood. The Lassell ring, named for William Lassell, who discovered Triton, occupies the region from about 53,000 to 57,000 kilometers from Neptune. This broad, faint ring actually consists of a uniform sheet of material rather than a narrow band, creating an extended zone where dust particles orbit the planet. The ring's outer boundary approaches the orbit of moon Larissa, suggesting interactions between the moon and ring particles may play a role in defining where the ring ends. The material composing Lassell is even more diffuse than in the other rings, making it barely detectable even in Voyager's carefully planned observations. A faint extension called the Arago ring may exist as a separate component at about 57,000 kilometers radius, though some researchers consider it part of the Lassell ring rather than a distinct structure. The uncertainty reflects the challenge of studying such faint features from limited observational data. Voyager 2 flew past Neptune only once, capturing images during a few hours of optimal geometry, leaving many questions about ring structure unresolved. Ground-based observations before and after Voyager provided additional data, but could not resolve the detailed structure visible only to the spacecraft's cameras. The outermost ring bears the name Adams, after John Couch Adams, who independently predicted Neptune's existence mathematically around the same time as Leverrier. The Adams ring orbits at approximately 63,000 kilometers from Neptune, and it contains the most unusual feature of Neptune's entire ring system: concentrated arcs of material rather than a uniform distribution. These arcs occupy specific longitudes within the ring, appearing as bright clumps separated by regions of much lower particle density. The arcs have been given individual names: Liberté, Égalité, Fraternité, and Courage, following French themes in Neptune ring nomenclature. Ring arcs are theoretically unstable. Orbital mechanics predicts that concentrated material should spread out over time, forming a uniform ring rather than maintaining clumps. The persistence of Neptune's ring arcs therefore requires explanation. Some mechanism that prevents the spreading and keeps material confined to specific locations. The key lies in orbital resonance with Galatea, the moon orbiting just inside the Adams ring. The 42 to 43 resonance creates gravitational nudges at regular intervals that shepherd arc particles, preventing them from drifting in longitude. Without Galatea's influence, the arcs would gradually disperse and Neptune's rings would lack this unique feature. The particles making up all these rings appear dark, with albedos around 4 to 6%, similar to the inner moon's. This darkness indicates the particles consist of rocky or organic material, rather than bright water ice, like Saturn's rings. The dark color makes Neptune's rings extremely difficult to see, except when backlit by the sun, when even tiny particles scatter light forward efficiently. Voyager's images showing the rings in their full extent were taken with the Sun behind Neptune, creating conditions where the normally invisible rings stood out against the blackness of space. The source of ring material likely involves impacts on the inner moons by meteorites, comets, or debris from other collisions in the Neptune system. When a projectile strikes a moon at typical solar system velocities of several kilometers per second, it excavates material and launches it away from the moon's surface. Some of this ejecta escapes the moon's weak gravity and enters orbit around Neptune, gradually spreading out to form ring material. The dark color of the rings matches the dark surfaces of the inner moons, supporting the connection between moon surface material and ring particle composition. The rings require continuous replenishment because natural processes gradually remove particles over time. Solar radiation pressure pushes small particles outward, eventually carrying them beyond Neptune's gravitational influence, where they escape. Electromagnetic interactions with Neptune's magnetosphere can alter particle orbits, causing them to spiral into the planet's atmosphere, where they burn up. Impacts between ring particles fragment material into ever smaller pieces until particles become so small they are swept away. These removal mechanisms mean the rings we see today cannot persist indefinitely without new material being added from the moons. The timescale for ring evolution remains uncertain, but probably ranges from thousands to millions of years, depending on particle size and location. The entire visible ring system may be relatively young in astronomical terms, perhaps only millions of years old, rather than billions. If the rings are indeed young, this raises the question of whether we are observing Neptune during a special time when rings happen to exist, or whether the ring-moon system maintains a steady state with creation and destruction balanced over long periods. The answer likely lies somewhere between these extremes, with rings waxing and waning, but persisting in some form throughout much of solar system history. The relationship between moons and rings extends beyond simple material supply to include gravitational shaping of ring structure. The resonances that create Neptune's ring arcs demonstrate how even modest-sized moons can dramatically affect ring particle distribution through precise orbital relationships. Similar processes operate throughout Saturn's ring system, where dozens of moonlets shepherd and sculpt the rings into gaps, waves, and other structures. Neptune's system shows these processes operating at the edge of detectability, with faint rings and small moons creating subtle effects visible only to spacecraft visiting at close range. The rings orbit within Neptune's magnetosphere, the region where the planet's magnetic field dominates the environment. Charged particles trapped in the magnetosphere can interact with ring particles, gradually sputtering atoms off their surfaces and ionizing gas molecules in the sparse exosphere created by particle collisions. These interactions may slowly erode ring particles or alter their surface properties, though the rates remain poorly constrained by available observations. Future missions to Neptune could study these magnetosphere ring interactions in detail, revealing processes difficult to observe from the Voyager flyby data. Looking at Neptune's ring system from a distance, you would see only the faintest suggestion of structure around the planet. Barely visible gossamer bands extending outward from the equatorial regions. The Adam's ring arcs might appear as tiny bright spots moving through their orbits, concentrated clumps distinguishable from the background only through careful observation. The inner moons would blend into this faint structure, dark objects moving through dark rings against the planet's bright disk. Their presence revealed more by motion than by brightness. The entire system speaks to delicate processes, operating at the limits of stability, maintained by precise orbital relationships between moonlets and particles. Beyond these inner rings and moons, farther from Neptune than even Nereid's eccentric orbit carries it, several more small moons trace their distant paths through space. These outer, irregular satellites follow orbits so elongated and tilted that they barely seem connected to Neptune at all, their great distances and long periods marking them as captured wanderers from the outer solar system. In the outermost reaches of Neptune's gravitational influence, several small moons follow orbits so distant and irregular that they spend most of their time far from the planet, traveling paths measured in millions of kilometers rather than the thousands typical of regular satellites. These outer, irregular moons were discovered not by passing spacecraft, but through systematic surveys conducted from Earth using powerful telescopes and sensitive detectors in the early 2000s. Each discovery added a new member to Neptune's family, revealing a scattered population of captured objects that tell stories about the chaotic early solar system when planets still influenced distant reaches of their neighborhoods. Halimede orbits Neptune at an average distance of roughly 16 million kilometers. Though its eccentric orbit means this distance varies significantly during each circuit. The Moon completes one orbit every 1,979 days, taking more than 5 Earth years to travel around Neptune once. The name Halimede comes from Greek mythology, one of the Nereids, or sea nymphs, following the naming convention for Neptune's moons, drawing from mythological figures associated with Poseidon and the sea. The Moon itself measures perhaps 60 kilometers across, too small and distant for detailed study, even with the best current telescopes. The orbit of Halimede is inclined about 134 degrees to Neptune's equator, meaning it orbits backward in a retrograde direction, similar to Triton, but from much farther away. The inclination and eccentricity clearly mark Halimede as a captured object, rather than a moon that formed from material around Neptune. The capture likely occurred billions of years ago, when more objects wandered through the outer solar system, some passing close enough to Neptune with just the right velocity to be gravitationally captured rather than deflected back toward the Kuiper Belt or interstellar space. Sao follows an even more distant orbit, averaging about 22 million kilometers from Neptune, with an orbital period of about 2,900 days, or roughly 8 Earth years. This moon orbits prograde rather than retrograde, traveling in the same direction as Neptune's rotation, though from such a distance that the planet's rotation becomes almost irrelevant to the dynamics. The orbital inclination of about 53 degrees places Sao far from Neptune's equatorial plane, tilting the orbit into Neptune's polar regions rather than circling the equator. The size is estimated at roughly 44 kilometers diameter, making Sao somewhat smaller than Halimede. Laomedea represents the smallest of Neptune's known outer moons, at perhaps 42 kilometers across, orbiting at approximately 23 million kilometers from Neptune. The orbital period is about 3,400 days, roughly 9.3 Earth years per circuit. Like Halimede, Laomedea orbits retrograde with an inclination around 135 degrees, suggesting similar capture circumstances, or possibly even a connection between the two moons. Some researchers have speculated that Halimede and Laomedea might once have been a single object that broke apart, though the evidence remains circumstantial, based mainly on their similar orbital parameters. The orbital elements of these outer moons show sufficient similarity within groups to suggest family relationships, where multiple objects share a common origin. The collision of a larger captured object with another moon, asteroid, or comet could have created fragments that now orbit as separate satellites while maintaining similar paths. Alternatively, tidal disruption during close approach to Neptune could have pulled apart a loosely bound binary object, creating two satellites from one parent. The data available cannot definitively distinguish between these scenarios, without more detailed observations of composition, surface properties, and precise orbital evolution. Samatz orbits even farther from Neptune than the previous moons, at an average distance of about 46 million kilometers, with an orbital period of roughly 9,100 days, or 25 Earth years. This tremendous distance places Psamathe at the edge of Neptune's sphere of influence, where perturbations from the Sun and other planets can significantly affect the orbit over long timescales. The orbital eccentricity of about 0.47 means Psamathe's distance from Neptune varies from about 25 million to 67 million kilometers during each orbit. The inclination around 126 degrees indicates retrograde motion like most of Neptune's outer moons. Psamathe measures roughly 40 kilometers across, based on brightness estimates and assumptions about surface reflectivity. Like all the outer moons, Psamathe's surface has never been imaged in detail, leaving composition and features unknown beyond what can be inferred from brightness and color measurements. The moderate albedo of perhaps 0.15 suggests a surface composition mixing ice with darker material, similar to many Kuiper Belt objects, and consistent with the theory that these moons originated in that region before being captured by Neptune. The most distant moon currently known to orbit any planet circles Neptune at the truly remote average distance of 48.4 million kilometers. Neso, named for another mythological Nereid, completes one orbit every 9,660 days, approximately 26.5 Earth years. This extraordinary orbital period means that someone observing Neso in the year 2000 would only now be seeing it return to roughly the same point in its orbit relative to Neptune and the stars. The distance is so great that Neso's gravitational binding to Neptune is quite weak, making the orbit susceptible to perturbations from passing objects or long-term changes in the Sun's influence. From Neso's distant vantage point, Neptune appears as a blue dot roughly 10 times brighter than the brightest stars, but far smaller than the impressive disk visible from inner moons like Proteus. The Sun, though greatly dimmed by distance, still shines brighter than Neptune as seen from Neso, making the solar system's central star more prominent than the planet the Moon ostensibly orbits. This creates an unusual situation where Neso's environment is more influenced by solar radiation and the distant reaches of the solar wind than by anything Neptune-specific, except the long-range, gravitational tie that keeps the Moon bound. The orbits of these outer moons are not perfectly stable over extremely long timescales, with perturbations from various sources slowly altering orbital parameters. over millions of years. The sun's tidal forces create a slight but continuous influence, as do the gravitational pulls of Uranus, Saturn, and Jupiter during certain geometric alignments. Passing stars, though extremely distant, can theoretically perturb orbits at these extreme distances, where Neptune's gravitational influence weakens. The net result is that these moons may eventually escape Neptune's gravitational control, be captured by another planet, collide with each other, or even impact Neptune itself given enough time. The question of how many outer irregular moons Neptune actually possesses remains open, with current surveys likely having found only the brighter and larger members of the population. Statistical models based on observed populations suggest dozens or even hundreds of small moons may orbit Neptune in these distant, irregular orbits, most too small and faint to detect with current technology. Each new generation of powerful telescopes pushes the detection threshold fainter, revealing new members of Neptune's extended family and filling in the size distribution of captured objects. The outer moons contribute almost negligibly to Neptune's total satellite mass, with all of them combined into perhaps 1/10,000th of Triton's mass. Their scientific importance lies not in their mass, but in what they reveal about Neptune's gravitational reach, about capture dynamics in the outer solar system, and about the population of small bodies wandering beyond the giant planets. Each moon represents an object that took a particular path through the early solar system, approached Neptune with a specific velocity, and experienced gravitational interactions that resulted in capture rather than deflection or collision. The temperatures on these distant, dark moons can barely be distinguished from the background temperature of space itself, perhaps 35 to 40 Kelvin, depending on albedo and distance from the sun. At these temperatures, essentially all substances except hydrogen and helium exist as frozen solids, creating worlds where chemistry operates at timescales of geological eons. The weak solar heating drives almost no activity, and the lack of internal heat sources means these moons have been geologically dead since formation. They simply exist, dark and cold, following their long elliptical paths in the outer darkness. Looking back at this collection of outer irregular moons, Halimede, Sao, Laomedea, Samate, Neso, the overwhelming impression is one of lonely isolation, objects scattered across distances larger than many planetary orbits. They connect to Neptune only through invisible gravitational threads, spending most of their time far from the blue planet in cold isolation. Yet they remain bound, completing their decades-long orbits before returning to periapsis, momentarily approaching Neptune before heading outward again. And the discovery of these distant wanderers required patient observation and technological advances that transformed astronomy in the decades since Neptune itself was first found. The story of how humanity discovered Neptune's family of moons unfolds across more than a century and a half, beginning only 17 days after Neptune itself was first observed through a telescope. William Lassell, an English brewer and amateur astronomer who built one of the finest telescopes of his era, pointed his instrument toward Neptune on 10th October 1846 and detected a faint companion orbiting the newly discovered planet. This companion, which Lassell initially called simply the satellite of Neptune, would later be named Triton. Becoming the first moon discovered around Neptune, and the last major moon to be discovered in the solar system before the 20th century brought new technologies and techniques. Lascelles' discovery of Triton came remarkably quickly after Neptune itself had been found through the mathematical predictions of Urbain Le Verrier and John Couch Adams, whose calculations indicated where a planet must exist to explain perturbations in Uranus's orbit. The discovery of Neptune represented a triumph of mathematical astronomy, predicting an unseen world's location based purely on gravitational theory. Finding Triton so soon after detecting Neptune itself demonstrated that even mid-19th century telescopes could reveal details about distant planetary systems when those systems contained large, bright objects close enough to separate from the planet's glare. For over a century after Triton's discovery, Neptune was thought to have only this single moon, with no other companions detected, despite searches by astronomers using progressively larger and better telescopes. The breakthrough came on May 1949, when Gerard Kuiper, the Dutch-American astronomer, after whom the Kuiper Belt is named, discovered a second moon using the 82-inch telescope at McDonald Observatory in Texas. This new moon, eventually named Nereid, appeared as a faint point of light moving slowly against the background stars during Kuiper's photographic observations. Nereid's faintness and eccentric orbit had kept it hidden until telescope technology advanced sufficiently to detect such dim objects. The gap between Nereid's discovery and the next additions to Neptune's family stretched for 4 decades, a period during which astronomers suspected Neptune might harbor more moons, but lacked the technology to find them against the planet's overwhelming glare. Ground-based observations from Earth faced fundamental limits imposed by atmospheric turbulence and the contrast between Neptune's brightness and the faintness of any small nearby moons. Only a spacecraft visiting Neptune could overcome these limitations by viewing the system from close range, without atmospheric interference, revealing moons too dark and too close to Neptune to detect from Earth. That spacecraft arrived in August 1989, when Voyager 2 completed its 12-year journey through the outer solar system with a flyby of Neptune. During the approach phase and the brief hours of closest encounter, Voyager's cameras systematically searched for new moons, discovering 6 that had remained completely unknown despite more than a century of telescopic observation from Earth. The discoveries included Nereid, Thalassa, Despina, Galatea, Larissa, and Proteus, ranging in size from roughly 80 kilometers to 200 kilometers across, all orbiting inside Triton's path. Proteus proved particularly surprising because its size makes it Neptune's second largest moon after Triton. Yet its proximity to Neptune and its dark surface had rendered it completely invisible to Earth-based observers. The discovery highlighted how much remained unknown about the Neptune system, despite decades of study, with the second largest moon only revealed when spacecraft carried cameras close enough to separate it from Neptune's bright disk. The find emphasized that many solar system objects might remain undiscovered simply because they orbit in locations or have properties that make ground-based detection nearly impossible. One of the inner moons, Larissa, had actually been detected earlier through an indirect method. On 24 May 1981, astronomers observing a stellar occultation when Neptune passed in front of a distant star noticed a brief dimming of the star before Neptune itself blocked it. This pre-occultation event suggested a moon or ring arc might exist near Neptune, but the observation could not be confirmed or repeated with other stars. The feature was designated tentatively as a ring arc until Voyager 2's images revealed the moon Larissa orbiting exactly where the occultation had indicated, confirming that the 1981 observation had genuinely detected the moon. After Voyager 2's encounter, attention turned to systematic surveys designed to find any additional moons that might exist in the outer reaches of Neptune's gravitational influence. These surveys used large ground-based telescopes equipped with sensitive electronic detectors called CCDs that could detect much fainter objects than photographic film. Teams of astronomers would image the region around Neptune repeatedly over several nights, then compare the images looking for faint points of light that moved relative to background stars, indicating they were orbiting Neptune rather than being distant stars themselves. These systematic searches bore fruit beginning in 2002, when a team led by Matthew Homan and others discovered 5 new moons in Neptune's outer, irregular population. The discoveries, announced in 2003, after confirmation observations verified the objects were indeed orbiting Neptune, included Halimede, Sau, Laomedea, Samath, and Neso. Each appeared as extremely faint dots in the images, detectable only through the careful comparison of multiple exposures taken on different nights, showing the objects had moved against the stellar background in ways consistent with Neptune orbits. The most recent addition to Neptune's known moon family came in 2013, when astronomer Mark Showalter discovered a tiny moon while studying archived images from the Hubble Space Telescope. Showalter was analyzing Hubble observations of Neptune's ring system, taken between 2004 and 2009, when he noticed a small white dot appearing in multiple images in approximately the same location relative to Neptune. Careful analysis showed the dot was a previously unknown moon orbiting very close to Proteus. The new moon, eventually named Hippocamp, measured only about 18 kilometers across, making it the smallest moon discovered around Neptune and one of the smallest in the entire solar system. The discovery timeline shows a clear progression from finding the largest and brightest moons first to detecting progressively smaller and fainter objects. As telescope technology advanced, Triton's size and brightness made it visible in 1846 with mid-19th century telescopes. Nereid, smaller and more distant, required the larger telescopes of 1949. The inner moons needed spacecraft cameras in 1989. The outer irregular moons awaited the large ground-based telescopes and CCD detectors of the early 2000s. Hippocamp required the Hubble Space Telescope and sophisticated image analysis in 2013. This progression suggests that Neptune almost certainly has additional moons awaiting discovery, particularly among the outer irregular population, where small dark objects could easily escape detection even with current technology. Each improvement in telescope sensitivity, detector technology, or image processing technique pushes the detection threshold fainter, revealing objects that were always there but simply could not be seen before. The current count of 14 confirmed moons likely represents an incomplete census, with the true total possibly numbering dozens or more. The naming of Neptune's moons follows International Astronomical Union conventions requiring names drawn from Greek and Roman mythology associated with Neptune or Poseidon. The first two moons received classical names: Triton after Poseidon's son, and Nereid after the sea nymphs. The moons discovered by Voyager 2 were named for various figures from Greek myth: Naiad for the freshwater nymphs, Thalassa for the primordial goddess of the sea, Despina from a word meaning lady or mistress, Galatea for one of the Nereids, Larissa for a lover of Poseidon, and Proteus for the shape-changing sea god. The outer moons discovered in the 21st century continued the mythological tradition with names like Halimede, Sao, Laomedea, Psamath, and Neso, all names of Nereids from Greek mythology. Hippocamp broke slightly from the Nereid pattern, being named for the mythological sea creature that was part horse and part fish, but remained within the broader oceanic and Poseidon-associated mythological tradition. The naming preserves a thematic consistency across Neptune's moon system, while honoring the mythological heritage of the planet's own name. Looking across the century and a half, from Lascelles' discovery of Triton to modern-day surveys revealing tiny, distant moons, the story traces humanity's expanding knowledge of Neptune's satellite system through improving technology and persistent observation. What began as a single companion, revealed in 1846, has grown to 14 known moons, with more likely awaiting discovery. Each new moon adds detail to our understanding of how Neptune's system formed and evolved, how moons are captured from the outer solar system, and what populations of small objects exist in the cold reaches beyond the giant planets. And through all these discoveries, one spacecraft encounter stands as the most significant event in Neptune moon exploration. Voyager 2's flyby that transformed most of these objects from unknown to known in a single day. The spacecraft, called Voyager 2, launched from Earth on 20th August 1977, beginning a journey that would carry it past Jupiter, Saturn, Uranus, and finally Neptune over the course of 12 years. The mission design took advantage of a rare geometric alignment of the outer planets that occurs only once every 175 years or so, allowing a single spacecraft to visit multiple worlds by using gravitational assists from each planet to redirect its path toward the next. By the time Voyager 2 reached Neptune in August 1989, the spacecraft had traveled over 4 billion kilometers and revealed unprecedented details about 3 giant planets and their diverse moon systems. The approach to Neptune began months before the actual encounter, as Voyager's cameras started imaging the planet and its known moon Triton from increasing resolution. These approach images allowed mission planners to refine the flyby sequence, identifying interesting features to target and adjusting the spacecraft's path through tiny course corrections. The distance from Earth to Neptune at encounter exceeded 4.5 billion kilometers, meaning radio signals took over 4 hours to cross the Gulf one way, making real-time control impossible. Every action Voyager 2 would take during the encounter had to be planned in advance and uploaded to the spacecraft's computers weeks or months beforehand. The closest approach to Neptune occurred on 25 August 1989, when Voyager 2 passed only 4,950 kilometers above the planet's cloud tops, the closest the spacecraft would come to any planet during its entire grand tour. The proximity allowed detailed study of Neptune's atmosphere, magnetic field, and overall structure, while also positioning the spacecraft to pass near Triton about 5 hours later. The trajectory had been carefully calculated to achieve both close approaches while also carrying Voyager 2 southward out of the ecliptic plane toward interstellar space, a departure angle that would eventually take the spacecraft beyond the Sun's influence entirely. During the brief hours of closest approach, Voyager 2's instruments worked continuously, capturing images of Neptune's clouds, measuring magnetic field strength and direction, analyzing atmospheric composition with spectrometers, and recording radio emissions from the planet's magnetosphere. The data streamed back to Earth at 21.6 kilobits per second, a rate that seems incredibly slow by modern standards, but represented the maximum achievable across the vast distance with the spacecraft's 12-watt radio transmitter and 30-meter dish antenna. Every image required many minutes to transmit. Every measurement was precious because this single pass represented humanity's only close look at Neptune. The discoveries came rapidly during those hours. Neptune's atmosphere showed more dynamic weather than expected, with storm systems, bright clouds, and wind speeds exceeding those of any other planet. The magnetic field proved tilted and offset from Neptune's center, creating an unusual magnetosphere quite different from Jupiter's or Saturn's relatively orderly fields. The planet's rotation period was measured more accurately than ground-based observations had achieved, refining our knowledge of Neptune's basic properties. And 6 previously unknown moons revealed themselves in the carefully planned imaging sequences, doubling the known population of Neptunian satellites in a single day. The Triton encounter came approximately 5 hours after the Neptune closest approach, when Voyager 2 passed within 40,000 kilometers of the Moon's frozen surface. The spacecraft's cameras had been programmed to capture images as Triton grew from a distant point to a detailed world showing surface features, down to a few hundred meters across. The images revealed the pink nitrogen ice, the cantaloupe terrain, the lack of impact craters, and most spectacularly, the dark plumes of the active nitrogen geysers, shooting material up from the surface into the thin atmosphere. This evidence of geological activity surprised the scientific team, who had expected Triton to be frozen and dead. The data from Triton kept arriving as Voyager 2 departed Neptune's system. The spacecraft, now on a trajectory that would carry it away from the Sun forever. Images of Triton's far side came in, showing more terrain and helping scientists map roughly 40% of the Moon's surface from the images captured during approach and departure. Measurements of Triton's thin atmosphere revealed the surface pressure and composition, confirming nitrogen as the dominant gas and providing values that matched theoretical predictions about how such an atmosphere should behave. Temperature readings from the infrared spectrometer recorded Triton's extreme surface cold, establishing it as one of the coldest places ever measured in the solar system. The other newly discovered moons appeared in Voyager's images as dark, irregular objects, their surfaces barely visible against the blackness of space, but their shapes and sizes measurable from the light they reflected. Proteus emerged as Neptune's second largest moon, despite having been completely unknown before the encounter. Its darkness and proximity to Neptune's glare having hidden it from Earth-based telescopes. The smaller inner moons, Nereid, Thalassa, Despina, Galatea, and Larissa, revealed themselves in carefully planned images that searched predicted locations based on subtle perturbations observed in Neptune's ring structure. The ring system itself appeared more clearly than ever before in Voyager's images. The faint bands of material showing structure and variation invisible from Earth. The ring arcs in the Adams ring stood out as brighter concentrations, confirming ground-based occultation observations that had suggested such features might exist. Galatea's orbit and its relationship to the ring arcs provided the first direct evidence that moon-ring interactions could maintain such structures, a gravitational resonance holding material in place against the natural tendency to spread evenly. All of these discoveries emerged from less than 24 hours of intensive observation as Voyager 2 swept through the Neptune system at over 20 kilometers per second. The spacecraft's path carried it from approach through closest approach to departure, the changing geometry allowing different instruments to observe different targets in the carefully choreographed sequence. Every moment had been planned, every image scheduled, every instrument measurement timed to maximize the scientific return from this single irreplaceable opportunity to study Neptune and its moons up close. The images took days to fully transmit back to Earth, even at the maximum data rate. The 4-hour light time delay, meaning that pictures of the closest approach only reached mission control long after Voyager had already departed. Scientists and engineers at the Jet Propulsion Laboratory in California watched the images arrive line by line, building up from top to bottom as the data was assembled. Each new image revealed features never before seen, details that transformed Neptune and its moons from abstract concepts into real places with specific characteristics worth understanding. The scientific papers analyzing Voyager 2's findings began appearing within months and continued for years as researchers worked through the volumes of data returned. The images were studied for geological features, crater counts, color variations, and structural details that revealed each moon's history and composition. The spectroscopy data revealed atmospheric compositions, surface mineralogy, and thermal properties that constrained models of how these worlds formed and evolved. The magnetic field measurements challenged theories about how ice giant planets generate their fields and how those fields interact with surrounding space. More than 3 decades have passed since Voyager 2's encounter with Neptune, and the spacecraft continues to function as it travels through interstellar space, over 20 billion kilometers from Earth. The spacecraft still transmits data about the space environment beyond the Sun's influence, providing measurements of cosmic ray intensity, magnetic field strength, and particle populations in the region between stars. Voyager 2 officially entered interstellar space in November 2018, when instruments detected the boundary where the Sun's influence ends and the galaxy's begins. No other spacecraft has visited Neptune since Voyager 2, making that brief 1989 encounter still our only close examination of the system. Every detailed image of Neptune's clouds, every measurement of Triton's geysers, every discovery about the moon system comes from that single pass 3 decades ago. The data remains valuable, studied and restudied as new techniques allow fresh insights from old observations. But the limitations are clear. One flyby at one moment in Neptune's year cannot reveal seasonal changes, long-term variations, or details in the regions Voyager did not observe. The encounter demonstrated both the power of planetary exploration and its limitations when conducted through brief flybys. Voyager 2 answered fundamental questions about Neptune and its moons, while raising new questions that can only be addressed through return missions. The geological activity on Triton, the unusual orbit and composition suggesting captured Kuiper Belt origin, the complex interactions between moons and rings. All these discoveries pointed toward deeper mysteries that a few hours of observation could not fully resolve. Understanding Neptune's system completely will require going back with modern instruments and staying longer. Looking back at Voyager 2's achievement, the mission stands as one of the great accomplishments of robotic exploration. A single spacecraft visiting all 4 giant planets and revealing their diverse characteristics. The Neptune encounter marked the culmination of the Grand Tour, the final planetary system visited before Voyager departed the Sun's family forever. The legacy includes not just the scientific discoveries, but also the inspiration that comes from seeing distant worlds clearly for the first time, transforming them from astronomical objects into places we can understand. And looking forward, that legacy points toward the next steps in exploring Neptune and its fascinating collection of moons. The decades since Voyager 2's encounter have seen no spacecraft return to Neptune, despite the discoveries that highlighted the system's scientific interest and the questions left unanswered by a single brief flyby. The distance presents a fundamental challenge. Neptune orbits roughly 30 times farther from the Sun than Earth does, placing it 4.5 billion kilometers away at closest approach. This distance means that even traveling at typical spacecraft velocities of tens of kilometers per second, the journey requires 12 to 15 years one way. A duration that tests both technology and the patience of mission planners waiting for results. The energy required to reach Neptune and enter orbit around the planet exceeds what chemical rockets can provide without multiple gravity assists from inner planets along the way. These assists extend the mission duration further as the spacecraft follows a winding path through the inner solar system before finally heading outward. The Voyager missions use Jupiter and Saturn assists to reach Uranus and Neptune, but entering orbit rather than flying past requires additional energy to slow down upon arrival. This necessitates carrying more fuel or using more efficient propulsion systems, adding mass and complexity to an already challenging mission. Proposals for Neptune missions have been submitted to NASA and ESA multiple times over the past 2 decades, each one advocating for return to this distant system with modern instruments. One concept focused specifically on Triton, recognizing the Moon as perhaps the most scientifically compelling target in the outer solar system beyond Jupiter's Europa. The proposed Trident mission would have orbited Triton, studying its geology, geysers, atmosphere, and interior structure over an extended period rather than the few hours Voyager had available. Such a mission could search for evidence of a subsurface ocean, map the entire surface at high resolution, and observe seasonal changes in geyser activity. Another concept envisioned a Neptune orbiter that would study the planet itself while also observing all its moons over multiple orbital periods. This approach would allow comparative studies of how different moons have evolved in the same environment, from active Triton to ancient Proteus to the small irregular satellites in distant orbits. The orbiter could observe Neptune's atmosphere through multiple seasons, tracking storm systems and cloud patterns as they evolved. The rings could be studied in detail, revealing their structure, composition, and the interactions with shepherd moons that maintain ring arcs. The scientific questions motivating these proposed missions include fundamental issues about Triton's interior and the potential for a subsurface ocean beneath the frozen surface. The geological activity visible in the geyser plumes suggests internal heat, but whether this heat is sufficient to maintain liquid water at depth remains unknown. If an ocean exists, it would make Triton potentially habitable, in ways similar to Jupiter's Europa or Saturn's Enceladus, places where liquid water contacts rock and energy is available to drive chemistry. Confirming or ruling out such an ocean requires measurements of Triton's gravity field and magnetic properties that can only come from an orbiter. The origin of Triton and the timing of its capture remain uncertain, despite the strong evidence that the moon came from the Kuiper Belt. Did the capture occur early in solar system history, when many objects still migrated through the outer regions, or did it happen more recently? How did the capture mechanics actually work? And what became of Triton's potential binary companion if that theory is correct? Understanding these questions would illuminate not just Triton's history, but also the processes that shaped the entire outer solar system during its formation and early evolution. The other moons raise questions of their own, particularly whether they represent remnants of Neptune's original satellite system or formed from debris after Triton's capture disrupted that system. The small inner moons could be fragments from larger bodies destroyed in collisions, their irregular shapes and dark surfaces consistent with such an origin. Studying their compositions and internal structures would reveal whether they share a common origin or represent diverse objects brought together by Neptune's gravity. Even understanding something as basic as what these moons are made of requires closer observation than Voyager could provide. The technology available for a modern Neptune mission far exceeds what Voyager carried in the 1970s and 80s. Modern cameras can capture images with much higher resolution and sensitivity, revealing surface details down to meters or even centimeters rather than the hundreds of meters Voyager achieved. Spectrometers can analyze light across broader wavelength ranges with better precision, identifying specific minerals and compounds that Voyager's instruments could not distinguish. Magnetometers and gravity measurement systems have improved enormously, providing data quality that makes detecting subtle features like subsurface oceans more feasible. Communication technology has also advanced, with more powerful transmitters and more sensitive receivers allowing higher data rates across the vast distance to Neptune. Where Voyager managed 21.6 kilobits per second, a modern mission might achieve hundreds of kilobits per second or more, meaning images and other data would return to Earth much faster. The improved data rate allows more ambitious observation programs, more images, and higher resolution measurements without overwhelming the communications system. Everything learned could be transmitted back within reasonable time frames rather than requiring days to send single images. The challenge remains finding the funding and political will to commit to a mission whose results will not appear for 15 or 20 years, from approval to first science return. Space agencies must balance priorities between different destinations, with Mars, Jupiter's Europa, and Saturn's Enceladus all competing for limited resources. Neptune is farther, harder to reach, and less immediately compelling to some than these closer targets, where the case for potential habitability is already established. The scientific community must make the case that Neptune's system deserves priority, despite the time and expense involved. Some researchers argue that Triton represents a Kuiper Belt object we can study up close, offering insights into the composition and structure of that distant population of icy worlds. Pluto has been visited by New Horizons, revealing a surprisingly complex and active world. But Pluto is only one example. Triton provides a second data point, allowing comparison and helping scientists understand what is typical versus what is unique among large Kuiper Belt objects. The captured nature of Triton means it formed in similar conditions to Pluto, but has since been modified by billions of years near Neptune, creating a natural experiment in how environments shape evolution. Looking beyond currently proposed missions, concepts for even more ambitious exploration include landers that would touch down on Triton's surface and conduct detailed chemical analysis of the nitrogen ice and dark geyser materials. A lander could observe geyser eruptions from ground level, measuring their composition, velocity, and duration directly rather than inferring these properties from orbital observations. The lander could drill or melt through surface ice to sample material from depth, analyzing layers deposited over millions of years. Such a mission would be extraordinarily challenging given the cold and the distance, but not impossible with sufficient technological development. Farther into the future, concepts exist for submarines that could melt through ice to reach subsurface oceans if they exist, or for aerial vehicles that could fly through Neptune's atmosphere, studying clouds and chemistry from within rather than from above. These ideas remain speculative, decades away from practical development, but they illustrate the long-term vision scientists hold for exploring the outer solar system. Each generation of missions enables the next, developing technologies and building knowledge that makes future steps possible. Eventually, humanity may develop the capability to explore Neptune's system as thoroughly as we now explore Mars. The wait for future missions means that Neptune's moons continue orbiting largely unobserved, except through ground-based telescopes that can reveal only limited information. Triton's geysers still erupt when summer brings sunlight to the southern hemisphere, depositing dark streaks across the pink nitrogen ice. The cantaloupe terrain remains unchanged, preserving its mysterious dimpled texture. Proteus continues its close orbit, its giant Pharos crater still the most prominent feature on its dark surface. Nereid follows its eccentric path, swinging close and then far from Neptune over the course of each Earth year. The small inner moons orbit in their tight cluster between Neptune and Proteus, invisible from Earth, but present in the Voyager images that captured them decades ago. The irregular outer moons trace their distant tilted paths, some prograde and some retrograde, barely bound to Neptune gravitationally. NASO continues its 26-year orbit at the edge of Neptune's influence, the most distant known moon of any planet. All these worlds persist in configurations they have maintained for millions or billions of years, following the physics of gravity and orbital mechanics, regardless of human observation. Earth-based astronomy continues to monitor Neptune when possible, telescopes tracking the planet's position and occasionally observing its brighter moons. New irregular satellites might still await discovery in distant orbits, too small and faint for current surveys, but potentially visible to future telescope generations. Advanced adaptive optics systems on large ground-based telescopes can now resolve Triton as a disk rather than a point, allowing rough surface mapping of major features from 4.5 billion kilometers away. These observations cannot match spacecraft data, but they maintain some continuity of observation between Voyager's encounter and whatever mission eventually returns. The exploration of Neptune's moons remains an unfinished story, one chapter written by Voyager 2 and the rest waiting for future missions to continue. What we have learned shows a system rich in diversity and scientific interest, from the active geology of captured Triton to the collisional family of inner moons, to the distant, irregular satellites barely holding their orbits. Each moon represents a different outcome of the processes that shaped the outer solar system. Different compositions, different formation mechanisms, different subsequent evolution. Together, they provide a laboratory for understanding planetary science across a range of conditions and histories. Tonight, Neptune continues its stately path around the distant sun, taking 165 Earth years to complete each circuit as it has for billions of years. Triton orbits backward, the only large moon to do so, its frozen surface erupting with geysers when seasons allow. The other moons trace their various paths, some close and some distant, some regular and some eccentric, each one contributing to the complex architecture of Neptune's satellite system. Our understanding of these worlds comes mostly from one spacecraft's brief visit decades ago. Images and measurements that transformed distant points of light into places with geology and atmospheres and stories. Someday, perhaps within the next few decades, another spacecraft will make the long journey from Earth to Neptune, carrying instruments far more capable than Voyager's. That mission will reveal details we cannot currently know, answering questions while raising new ones, as exploration always does. The geysers of Triton will be observed continuously, rather than glimpsed briefly, their mechanisms understood, rather than inferred. The moon's compositions will be measured precisely, their interiors probed through gravity and magnetic studies, their surfaces mapped completely. Neptune's system will transform from partially explored to well understood, joining Mars and Saturn as places we know thoroughly rather than superficially. Until that time arrives, we have the knowledge Voyager provided and the patience to wait for more, the moons continuing their orbits in the cold outer solar system. Worlds waiting at Neptune's distance for the next visitors from Earth to come and see what has changed and what remains the same across the decades. The journey ahead is long, measured in years of flight time and years of planning before that. But the discoveries waiting make the patience worthwhile. Neptune's 16 moons hold secrets about the outer solar system, about planetary formation, about how ice and rock and organic compounds behave under conditions found nowhere else we can easily reach. And in time, we will return to learn what they have to teach.